Hello everyone, welcome back to my YouTube channel. Let's encode the logic. I hope you all are doing good. In today's video, we are going to discuss about bitwise operators. This is the part 2 of the video. I have already uploaded the part 1 of the video. There I discussed about the binary conversion of a decimal number and the most significant bit and the least significant bit and the negative number binary conversion and one's complement, two's complement calculation, the rules, and also the professional way of converting a decimal number to a binary number. So before watching this video, I request you to watch the part 1 because in this video, we are going to use those terminologies which I have explained in the part 1. I will provide the link in the description box. Please do watch it and then continue this video. So we know in Python, we have bitwise AND, bitwise OR, bitwise XOR, bitwise NOT. So what is bits? By the name itself, we can say that it was formed with zeros and ones. Then how to compute this bitwise AND, bitwise OR, bitwise XOR, bitwise NOT on numbers? So that was the question. Okay, let's consider two numbers. That was 26. The binary conversion of this number was 11010. And 17, that was 1001. So these are the binary representation of the numbers 26 and 17 respectively. And this is the truth table. Basically, this truth table consists of all the possible cases and some results. And we will build the possible cases with zeros and ones. And the possible cases are, so both the operands are ones, and the left operand is 1 and the right operand is 0, and the right operand is 0 and the left operand is 1, and both the operands are zeros. And now the bitwise AND. The rule of bitwise AND operator was, if any one of the bit was 0, then the result will be 0. If you see the first one, A and B. So let's take this case 1, that was both the bits are 1s. We will do 1 and 1. So none of the bit was 0, right? So simply the result was 1. And the next case was 1, 0. And we do 1 and 0. So this bit was 0. So the final result will be 0. And 0 and 1, this bit was 0. Final result will be 0. Here the both bits are 0. The final bit was 0. Next one was A, bitwise OR B. So the rule for the bitwise OR was, if any one of the bit has 1, then the result will be 1. So if you consider this first case, 1 and 1, here both are 1, so the result will be 1. Here 1 and 0. So the rule was that at least one bit has 1. So here A equal to 1, so the final result will be 1. So here the B equal to 1, at least one bit has 1. So it was 1. And here both are zeros. There is no ones in this case. So the result will be 0. And coming to A bitwise OR B. The rule for this bitwise OR was, if both the bits are same, then the final result will be 0. If both the bits are different, and the final result will be 1. If you see A and B, the bits are 1, 1. Both bits are same, 1 and 1 are same. So the result was 0. Here the different, both bits are different, 1, 0. So the result was 1 and 0, 1. The result was different. So the bits are different. So the result was 1. And here 0 and 0, the both bits are same. The result was 0. In this way, we will compute the A and B, A or B, A XOR B, and those are the rules for A and B, A or B, A XOR B. Now, we need to compute this A bitwise and B, A or B, A XOR B on this 2617 binary representation. Okay, let us do 26 and 17 first. So we need to start from the least significant bit and till the most significant bit. Okay, 0 and 1. 0 and 1 was 0. And 1 and 0, that was also a 0. And 0 and 0, of course 0. And 1 and 0, this was 0. And 1 and 1, that was 1. This is the result of 26 and 17, bitwise and 17. And next step, we need to do 26 or 17, bitwise or 17. So here 0 or 1 will be 1. Any one of the bit was 1, it will be 1. And then 1 or 1, 1 or 0, that was 1. And the 0 or 0, that was 0. And 1 or 0, that was 1. And 1 or 1, this was 1. So this is the final result of 26 bitwise or 17. And we need to do 26 or 17, right? 26 or 17. So 0 or 1, here both are different. So the result will be 1. And 1 or 0, that was 1. And 0 or 0, both are same bits. So the result will be 0. And then 1 or 0, 1. And here 1 or 1, both are same. So the result will be 0. So this is the result of 26 or 17. Okay, now let's do the decimal conversion of this binary representation. So that was, this was 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. So this was 16. The result was 16. So if we compute 26 bitwise and 17, the result will be 16. Okay. And this was 2 power 0 plus 2 power 1, 3. And 3 plus 2 power 3, that was 3 plus 8, that was 11. 11 plus 16, it was 27. We got 27 now. And this 2 power 0 plus 2 power 1, 3. And 3 plus 2 power 3, that was 8. 3 plus 8, that was 11. In this way, we will do calculate. So, okay, let's work on them on the ideally. I have a num1 that was 26 and num2 that was 17. And if I do num1 and num2, what should I need to get? I need to get 16, right? So the result was 16. And I will do num1 bitwise or num2. What should I need to get? I need to get 27. So I got 27. And num1 or num2. So my answer should be like 11. So I got it. Okay. And also we have a predefined formula for bitwise OR. So the formula was A XOR B will be A B negation plus BA negation. Let us consider the first case, that was A equal to 1 and B equal to 1. My A will be 1 into B bar, nothing but B negation. So if I compute a 0 bar, then it will be 1 and 1 bar will become 0. Okay. So B is 1. So B bar will be 0 plus B was 1 into A bar. A was 1. So A bar will be 0. So 1 into 0 plus 0 into 1 will be 0 itself. Let us take the second case. A will be 1 and B will be 0. I will do A equal to 1. B will be 0, right? 0 bar will be 1. Plus, okay, B 0 into A bar. 1 bar, that was 0. So 1 into 1 plus 0 into 0, that will be 1. So if you observe, 1 bitwise or 1 will be 0 and 1 bitwise or 0 will be 1. So in this way, we can compute this bitwise OR also. This is the formula for bitwise OR. That was A B bar plus B A bar. And the next operator was bitwise NOT. And this is the symbol for bitwise NOT. So this bitwise NOT operator will return the ones complement of the number. So if you observe, here we have used two operands, A and B, A or B, A XOR B. But here we have used only single operand, right? Let us have a number that was some 10. Then I will do bitwise NOT of A. This bitwise NOT symbol will be found below the escape button in the keyboard, okay? And I will do bitwise NOT of A. I got minus 11. So how do we get this minus 11 from this A equal to 10 if we do bitwise NOT? So now consider A equal to 10 and the binary representation of this 10 was 1 0 1 0. So 2 power 1 plus 2 power 3, 8 plus 2, that was 10. So in the computers, it follows 32-bit format like 0 0 and some after 1 0 1 0. And if we convert this binary representation into one's complement of this binary representation was, the rule was 1 will be converted to 0 and zeros will be converted to 1. So all these zeros will be converted to ones, and after several ones, we will get this result 0, 1, 0, 1. So if you see, the 0 was converted to 1. Since the bitwise negation inverts this sign bit, we now have a negative number. If you observe what I said in the previous video, that part 1 video, I told that the positive number is represented with the 0 as the most significant bit, and also if it was a negative number, the most significant bit will become 1, right? And if you see, have converted this binary representation to 1's complement, and my final result, the most significant bit was 1. So this was a negative number. And how do we represent a negative number? We represent a negative number using 2's complement, right? We need to do the 2's complement of this result. For the simplicity purpose, let's take this part only. We need to do the 2's complement of 0, 1, 0, 1. Right? For that, at first we will do 1's complement plus 1. 2's complement formula was 1's complement plus 1. And the 1's complement will be 1, 0, 1, 0 plus 1. Right? The result will be 1, 0, 1, 1. So if we compute this, if we convert this binary number to the decimal number, so that will be 2 power 0 plus 2 power 1 plus 2 power 3, 8 plus 2 plus 1. That was 11. And this is a negative number, as I said before. This is the negative number representation. So we'll keep minus 11. I hope you got this. In this way, we got minus 11 here. So this is the calculation of bitwise NOT. So the step 1 was, we did 1's complement of that number. And the second step was, we got to know this was a negative number. This first step is a negative number. So we represent the second number in the 2's complement. And we did 2's complement of this A. Right? B equal to some 2's complement is A. And since this is a negative number, the final result will be minus B. So this is the steps for the bitwise NOT operation. And we also have 2 more operators. They are left shift operators and right shift operators, which will work on the bits only. So this is the right shift operator and this is the left shift operator. If you see, this is the head and this head is pointing towards the right side. And if you see, this is the head and this is pointing towards the left side. That's why this is the left shift operator and this is the right shift operator. So how this left shift operator and right shift operator works? Let us have an example of 26 again. That was 1, 1, 0, 1, 0. I will do the left shift of 1. The meaning of this expression was, I want to shift the bits in this binary number 1 position left side. So basically this number will be like, let us consider the 8-bit representation. The final output will be, so this bit 0 will be shifted to here. So 0 and this 0 will be shifted to here. And this bit 1 will be shifted to here. That was 1 and 0, 1, 0. And if I want to shift the same one with 2 bits left, then I will keep 2 here. So this 0 will be shifted to 2 bits left and this 0 will be shifted to 2 bits left and this 0 will come here. And this one will come here. And next this one and 0, 1, 0. So if we compute this, 2 power 0, 2 power 1, so 2 square plus 2 power 4 plus 2 power 5. 32 plus 16 plus 4. Nothing but 52. So this was 52. And so this will become 0, 0. And this was 2 power 3. 2 power 3 plus 2 power 5 plus 2 power 6. Nothing but 128 plus 32 plus 8. 168. So this is about the left shift operator. Okay, now let me do the right shift operator. The same example that was 26, and I will took the same 0 1 1 0 1 0. Right shift 1. If I do compute this, the bits will be shifted to one position right. So this 0 will come here. So that was 0, and this 0 will come here. So 0, and this 0 will come here, 0, and 1 will be come here, and 1, and then 0, 1, and 0. So we can't use this. Basically, we can't keep this, and now this 0 will be ignored, and we keep a 0 here. In this way, we will shift the bits. And if we compute this, we will get 2 power 0, that was 1 plus 4 plus 8, that was 13. And if I want to do the right shift for 2 bits right, I'll do this, and this 0 will come here, and then 0 0 1 1 0, and I need to ignore this 2 bits. This 1 0 will be ignored, and this final result will be 2 power 1 plus 2 power 2, that was 2 plus 4, that was 6. So let's quickly run them on this. Ideally, I have the number equal to 26, and I will do 8 left shift 1. Then I got 52. If you see, I got 52, and I will do A left shift 2. Then I got 104. I think I made some calculation mistake. So yeah, I did a mistake. That was 8 plus, so here 2 power 3, 8 plus 2 power 5, 32. 32 plus 2 power 6, that was 64. 8 plus 32 plus 64, that was 104, not 168. So this was 104. Yeah. And then I will do A right shift 1. I got 13. And I will do A left shift 2. Sorry, A right shift 2, that was 6. And if you observe here, in the first one, I did 26 left shift 1. Then my result was 52. So what happened? We got 26 into 2, that was 52. And again, I did 26 left shift 2. And here, we got 26 into 4, that was 104. So every time, the result was multiplying. In the first case, 26 into 2, we got 52. And then 52 into 2, we got 104. We can say this left shift operator will use us into. Every time it will be multiplied with 2 whenever we shift the bits to the left side. And if you observe here, the right shift operator, the 26 will become 13. Right? So it means 26 divided by 2. If I do 26 divided by 2, I got 13. And if I do 13 divided by 2, I got 6. So this right shift operator will use the division. So in this way, the left shift operator works and the right shift operator works. So this is about the bitwise operators, the bitwise AND, bitwise OR, bitwise XOR, bitwise NOT, and the left shift operator and right shift operator. So I hope you like this video, and thank you for watching. Hey folks, if you enjoyed this coding tutorial and found it helpful, don't forget to give it a thumbs up. Share it with your fellow coding buddies, drop a comment with your thoughts or questions, and of course, hit that subscribe button and ring the notification bell so you never miss out on our latest content. Your support means a lot and it helps our community grow. Happy coding!